Notes and tricks. Learn faster. Score higher.
You ever wonder if there's like a secret code baked into every single number, a fundamental rule that not only builds every number we can think of, but also helps us prove that some numbers, well, they just go on forever? Let's crack that code. So how can one single rule do all that? That's exactly what we're going to dig into. We're going to explore one super powerful theorem that's kind of like a master key to the world of numbers. And then we'll use that key to solve a mystery that's had mathematicians hooked for centuries. Okay, first things first, let's talk about this secret code. It's this idea that every number, I don't care how massive or complicated it looks, is actually built from the same basic ingredients. And here it is, the big one, the fundamental theorem of arithmetic. I know it sounds a little formal, a little textbooky, but just focus on two key words here, product of primes and unique. That's the whole game. It's basically a two-part promise. 1, every number that isn't already prime is just a bunch of primes multiplied together. And 2, there's only one specific recipe of primes for each number. The easiest way to think about it is like this. Prime numbers, 2, 3, 5, 7, and so on, they're like the Lego bricks of the number universe. They're the most basic pieces. You just can't break them down any further. And this theorem, it guarantees that any number you build, let's say the number 12, will always be made from the exact same combo of bricks, 2 2s and 1 3. It's got its own unique blueprint, its own numerical DNA. No other recipe of primes will ever give you 12. Okay, so this isn't just some cool theory to talk about. This is an incredibly powerful toolkit and helps us solve all sorts of problems, especially the kind that love to pop up on exams. So let's put it to work with a classic problem. We need to find the highest common factor and the lowest common multiple, or the HCF and LCM, for the numbers 6 and 20. So what's the biggest number that divides into both? And what's the smallest number that both of them can multiply into? All right, first we break each number down to its prime blueprint. 6 is super easy, it's just 2 times 3. 20 is 2 times 2 times 5, or we can write that as 2 squared times 5. To get the HCF, the highest common factor, we just look for the prime Lego bricks they have in common. Well, they both have 1 2 brick, and that's it. So the HCF is 2. Done. For the LCM, the lowest common multiple, we need to build the smallest number that contains both of their blueprints. So we take the highest power of every single prime brick involved. We need the 2 2s from the 20, the 1 3 from the 6, and the 1 5 from the 20. Multiply those all together and you get 60. Let's kick it up a notch with a bigger example, 96 and 404. When we break them down, we find out 96 is made of 5 2s and a 3. 404 is 2 2s and a 101. So for the HCF, we ask that same question, what's the smallest power of the common prime factors? Well, the only prime they share is 2, and the smallest power they have in common is 2 squared. So the HCF is 4. And here is an absolutely awesome trick. For any two numbers, the HCF times the LCM is always equal to the two numbers multiplied together. So instead of going the long way to find the LCM of 96 and 404, we can just use this formula. It's just 96 times 404, all divided by the HCF we just found, which was 4. So much easier. Right, let's see how this stuff actually helps solve puzzles you might run into in the real world. Here's a classic word problem. You've got Sonia and Ravi running laps, but they're running at different speeds. They start at the same spot at the exact same time, so when are they going to be back at that start line together again? The answer is 36 minutes. But why? How did we get there? Well, think about it. This is a perfect job for the lowest common multiple. We're looking for the first time the lowest number of minutes that is a multiple of both 18 and 12. And the LCM of 18 and 12 is 36. That's when their paths line up again right at the start. All right, now for part 2 of our adventure. We've been building numbers up. Now we're going to prove some can't be built perfectly at all. It's time to put on our mathematical detective hats. Our mission, should we choose to accept it, is to prove that the square root of 2 is irrational. That just means it can't be written as a nice, clean fraction. And our method for doing this? It's a really clever technique called proof by contradiction. I want you to think of this like a courtroom drama. We're putting the square root of 2 on the witness stand, and we're going to assume it's innocent, or in our case, that it's rational. And we're just going to see if its story holds up under questioning. So step 1 is our big assumption. We say, okay, court, let's just pretend for a minute that the square root of 2 is rational. That means we can write it as a fraction, a divided by b. And, this is the most important part, we're saying that fraction is in its simplest form. A and b have no common factors. Next, we just do a little bit of algebra. We square both sides of the equation and move things around a bit. And we get this. A squared equals 2 times b squared. Now, just look at that. If a squared is equal to 2 times anything, then a squared itself has to be an even number, right? Okay, now here's a key piece of logic. If a number squared is even, then the original number has to be even too. You can't get an even square from an odd number. So if a squared is even, a must be even. And if a is an even number, we can just write it as 2 times some other whole number. Let's just call it c. And here comes the twist. We take this new definition of a as 2c, and we plug it back into our equation from a couple of steps ago. We do a little more algebra, and we end up with b squared equals 2 times c squared. But, wait a second, that looks familiar. That means b squared is also even, which means b has to be even too. And this is it. This is the moment the whole story falls apart. This is the fatal flaw in the testimony. We started this whole thing assuming that a and b had no common factors, but our own logic has forced us to conclude that a is even and b is even. That means they both have a common factor of 2. Our result completely contradicts our starting assumption. Case closed. As the source material says so perfectly, this contradiction happened for one reason and one reason only. Our initial assumption was just plain wrong. The square root of 2 can't be rational. Therefore, it must be irrational. So we've seen how one fundamental rule helps us build every number, solve puzzles, and even play detective to uncover these really deep truths. So the question I want to leave you with is this. Now that you've seen the method, you've seen the logic, could you put the square root of 3 on trial and prove its case?